Very good afternoon to all of you students, and this is our lecture number 2 from work energy power chapter. We already completed that is the introduction part, and in the last lecture we discussed about the work, the nature of work and derivation of work, calculation of work by graphical method when a constant and a variable force applied on a body. And this is our lecture number 2, and in this lecture we will discuss about energy. The definition of energy, unit, dimension, classification, and mainly here we will discuss a kinetic energy. We will prove kinetic energy expression. Then we will discuss very important theorem which is named as work energy theorem. We will prove work energy theorem. Then we will solve some important numericals related to energy, related to work energy theorem. So let's begin the class. First of all, you have to know the meaning of energy. I think all of you know this part. Energy is defined as it is a capacity or ability to do work. The capacity or ability to do work is known as energy. So energy is a form of work done. So obviously the expression of energy, the unit and the dimension of energy will be exactly same as the dimension and unit of work. So what is the SI and CGS unit of energy? SI unit will be joule and the CGS unit will be arc, and the dimension will be, write it. So first part, energy, at first you write the definition. Energy is defined as the capacity or ability of doing work. Energy is represented by symbol E, capital E. Okay, and the SI unit of energy, SI unit will be, that is exactly the unit of work, that is SI unit will be joule, and the CGS unit will be arc, and the dimension of energy will be, that is force mLt minus 2 into displacement. Energy is the capacity of doing work, so work is converted into energy. So this expression will be, you see, m L, so that is L square T to the power minus of 2. Now what is the quantity? Which quantity? Energy is a scalar or vector quantity? Obviously energy is a scalar quantity. Okay, so this is all about the basic part of energy. Now energy are various types. There is a mechanical energy, sound energy, light energy, chemical energy. There are a number of types, various types of energy. But here mainly we will discuss the mechanical energy. The energy mechanical and is classified in two categories. One is kinetic energy and another one is potential energy. Now in this lecture we will discuss about the kinetic energy, and in next lecture we will discuss the potential energy. So what is kinetic energy? Kinetic energy, that means when a body is under motion, the energy possessed by a body due to its motion, by the virtue of motion, the energy possessed by a body is known as kinetic energy. And what is the general expression? A body of mass m is moving with velocity v. Suppose a body of mass m moving with velocity v, then its expression of kinetic energy, that is k equal to half mv square. Now we will prove this expression in general method, and we will prove this expression by calculus method. So before going to that part, at first you see what is the example of kinetic energy. Due to motion, the energy, that is named as kinetic energy, and you see the example, write it. First one, a fast moving stone can break a window pane. Why? Because the moving stone, the stone is moving, so it has velocity. So energy expression, kinetic energy expression, k equal to half mv square. So when this has velocity, this has kinetic energy. So energy, that means there is some form of work done, that's why it can break the window pane. Okay, another one, a bullet fired from a gun can pierce a target because the bullet has kinetic energy, bullet has velocity. The kinetic energy of air is used to run windmills, all of you know. So these are the types of examples of kinetic energy. Now the expression, general expression of kinetic energy, that is half mv square. Now we will prove this expression by general method and calculus method. Okay, prove it. So first give the heading expression of kinetic energy half mv square by general method. So first point, that is half, we will prove half mv square general method. So suppose a body of mass m is placed on a horizontal surface and a force capital F is applied on the body, and for this case the body is moving along the direction of force. Suppose after time t the body's position, new position is here. So this is the displacement, this is the displacement, and suppose the body is initially at rest. So initial velocity u0, and after some time the body attains final velocity, which is named as v. Here the body is moving with velocity v. Okay, and the direction of force and the direction of displacement is same, along the same direction. So at first you write the, what is u? U is the initial velocity, right? Initial velocity. And here body is initially at rest, so the value of u here 0. What is F? F is the applied force. F is the applied force which acts on the body, and that's why the body displaces. What is S? S is the displacement. S is the displacement. What is V? V is the final velocity. V is the final velocity attained by the body after some time t. Okay, now we use this formula. You know the formula, v square equal to u square plus of 2as. This is equation of motion. We already completed this part in laws of motion chapter, sorry, in motion in a straight line. So here you see, here final velocity v, so this one v square, but initial velocity 0, body initially at rest, this condition body at under rest. So here this value is 0 plus 2as. So from here you can write a, that is equal to v square upon 2s. This is the acceleration. What is a? A is the acceleration which is attained by the body. Now what is the amount of work done? Amount of doing work is known as energy. So energy is a form of work. So here we will find out the amount of work, and this amount of work will be equal to kinetic energy. So find it. What is the work done for applying this force? So work done, you know the general formula of work done, that is W is equal to the dot product of F and S, that is F S cos theta. Now you see here F and S along the same direction, so theta is equal to 0 degree. So this value gives W equal to F into S. Now so W equal to, in the place of F you can write Newton's second law of motion, F that is equal to m into A. So write it m into A into S. Suppose this is our equation number 1. Now you use equation number 1, putting equation 1 in equation 2, that is m, and in the place of A you can write v square by 2s, and in the place of s you see s cancel out, so this equation becomes half m v square. This is the value of W, and this amount of work is converted into energy. So here kinetic energy attained by the body when moving with velocity v, that is k equal to half m v square. This is the proof of k equal to half m v square by general method. Now we will prove this equation by calculus method, when a variable force acts on a body. So what is the process? This one is the when a constant force acts on a body. A force, if this force is constant, but when a variable force acts on a body, what is the process for solving this equation? How to prove it? Okay. So for calculus method, at first you have to find out amount of work done, small amount of work done. So here we will prove this by calculus method. Calculus method. So suppose a force capital F applied on a body, and for this force a body displaced through a displacement del S. So for this del S displacement, what will be the amount of work done? dW, and that is will be F dot del S. Now use Newton's second law. According to Newton's second law, you can write F, that is equal to m into A. In the place of A, you can write dv by dt. The rate of change of velocity with time is known as acceleration. Okay. Now here you use, that is W equal to, in the place of F you write this one, that is m dv by dt, and there is ds. Now you see this equation becomes m del S by del T. This is a displacement by time. There is velocity, there is V into these values gives dV. Okay, you write this value in magnitude form. Okay, write it magnitude form. At first you see this one is F ds cos 0 degree. So this one will be F into ds. Why cos 0? Because the force and the direction of force and the displacement along the same direction. Okay, so this dw equal to F ds. Now for Newton's second law, F equal to m and A, that is dv by dt. Now this equation dw equal to m dv by dt into ds by dt, that is equal to v. So this one is m v into dv, and this value gives the amount of work done for the small displacement ds. So what will be the total amount of work done? You have to do integration. So the total amount of work done, right? Total amount of work done will be W equal to integration dW, that is integration m v into dv. And you see here body initially at rest, so the lower limit of velocity, that is 0, final velocity, that is v. Now integrate it, m constant outside, v into dv integration, you know the integration, v square by 2. Now lower limit 0 and upper limit v. Now you just use limit, that is W equal to, here m outside take, that is m by 2, there is in the place of v you have to use v, so that is v square minus now lower limit, that is 0 square. So the expression will be, you see, that is half mv square. So W, that is equal to half mv square. This is the expression of work done, and this amount of work done is converted into form of energy. So here kinetic energy K, that is equal to half mv square. Okay, so this is the another proof of K equal to half mv square, but this proof is by calculus method. Here you using integration. Okay, so this is all about the expression of energy. Now we will discuss another important part, that is the theorem which is named as work energy theorem. Write it. So keep the heading work energy theorem. Next part, that is work energy theorem, and after that we will solve some important numericals related to it. So next, write work energy theorem. You see the name, work energy theorem. You give the statement, work energy theorem states that the amount of work done, amount, right, amount of work done by all forces, this point is important student, by all forces, or you can write by the net forces, the amount of work done by all forces, that is exactly equal to change in kinetic energy, exactly equal to change in kinetic energy of a body. You see work energy theorem, that the amount of work done is equal to energy. Which energy? The change in kinetic energy. Here no potential energy. Okay, so the amount of work done is by all the forces. all the net forces amount of work done is equal to change in kinetic energy. And using this concept we can solve very high thinking problem easily. Okay, so write this formula in mathematics. Okay, amount of work done by all forces. Suppose, so this value is W, that is equal to, okay, here you write all forces, or you can say net force, that is change in kinetic energy. Suppose a body of mass m moving with initial velocity u, you can write this one. Suppose a body mass m moving with initial velocity u, after some time t the body attained final velocity v. So what is the expression of final kinetic energy? Change in kinetic energy, that means final kinetic energy minus initial kinetic energy. So final kinetic energy, that is half m v square minus initial kinetic energy, that is half m u square. So here you write, that is W is equal to, this is kf and this is ki. Kf, that means kinetic energy final, and Ki, that is kinetic energy initial. You can write this value. You see this one give del W. So del W, that is equal to, this is the change in kinetic energy which is named as del K. So del W is equal to del K. This is the mathematical form of work energy theorem. Okay, now we will prove this theorem by general method, that is when a constant force acts on a body, and we will prove this theorem when a variable force acts on a body, that is by calculus method. And the proof of this theorem and the expression of kinetic energy, which I already completed, is exactly same. In the expression of kinetic energy, there we use the initial velocity 0, but you see here initial velocity is present. The method is same, the proving method is same, but here you have to use initial energy u. Okay. So first of all, you see, if I prove this value in general method, if I write v square is equal to u square plus 2as, you see from here you can write v square minus u square, that is equal to 2s, right? Okay. Now you multiply both sides by m by 2. Okay, multiply it, multiplying both sides by m by 2. This one will be half mv square, this one will be half mu square, and this one is 2as m by 2. So 2 cancel. This one is kinetic energy final, this one is kinetic energy initial, and this one is, see, m into a, that is F according to Newton's second law, F, and this one is S. So this value gives the change in kinetic energy del K, and force into displacement. So this value gives the amount of work done. So this is the proof of work energy theorem by general method. At first you explain this part. Okay, then you write this one. Now we'll prove this formula with the help of calculus method when a variable force acts on a body. So for calculus method, at first you have to find out the small work done, dW, then you have to find out the total work done with the help of integration. Okay, solve it. So in calculus method, at first you write dW, that is F into ds, the amount of work done for displacement del S when a force capital F acts on a body of mass, the body mass, that is suppose m. So this value will be F ds cos theta, and suppose force applied, the direction of force and the direction of displacement same. A force applied on a body and the body displaced along the same direction of force, this one along the same direction of force. So this value will be F ds cos 0, so that is F into ds. Now total work done. So before going to that part, express this one, that is F equal to, according to second law, Newton's second law, right? Newton's second law, that is F equal to m into a, that is m a, that is dv by dt. Now putting this value dw equal to, in the place of F you write m dv by dt Method is same. Here you have to use limit, that is u to v, lower limit u and upper limit v, and we already completed, that is half mv square proved by calculus method, and there we use initial velocity 0. So F equal to m dv by dt, and this one is ds, so this one will be m, you see ds by dt, this value will be v, and there is dv. So total work done, that is w equal to integration dw, that is integration u to v mv dv. This is the difference between proving of half mv square and this one by calculus method. Here we use u and final velocity v. Okay, so now differentiate it. So this one is w, this one is m common, m dv, that is v square by 2, lower limit u, upper limit v. So w, that is equal to, this one is m by 2, and this value will be first of all v square minus of lower limit u, so this one is u square. So that is w is equal to half mv square minus of half mu square, that is w equal to, this one is kf minus of ki, that is w equal to del k. This is the proof of work energy theorem by calculus method. Okay, so this is all about theoretical part. Now we'll see important numericals, how to solve numericals related to work energy theorem. Okay, right, first numericals. Suppose a body of mass m, right? First numericals, problem 1, a body of mass m, that is equal to 2, okay, you write 3 kg. A body of mass m is equal to 3 kg acted upon by some force, right? Acted upon by some force, and okay, some force such that, right, such that the VT graph as shown in figure, as shown in figure. Okay, a body of mass 3 kg acted upon by some force such that VT graph is shown in figure. You have to find out work done, right? You have to find out work done by this force. Suppose this graph is given like this way. This is the velocity, meter per second, and this is the displacement, sorry, time t in second, and the graph is like this one. Suppose this value is 20 and this value is 5. You have to find out work done. Okay, find it. You know the formula for finding work done, and the formula is one formula, that is w equal to f into ds, and another formula, one formula w equal to f dot ds. But here you see the force is not given, acted upon by some force, the value of force is not given, so no need to this formula. But you know this one, that is w equal to del k, amount of work done by all forces is equal to change in kinetic energy. So work done, that is equal to change in kinetic energy, half mv square minus of half mu square. So w, that is equal to half, in the place of m you can write this one m, okay, 3 v square, v. What is v? You see, v is the final velocity. Here this axis gives the time, so this is the time 0. So when t is equal to 0, the velocity is named as initial velocity. T is 0, so initial velocity, this one 20. And when t is equal to 5 seconds, what is initial velocity? T equal to 5 seconds. So you see the velocity for 5 seconds, that is 0. So final velocity is 0. Initial velocity 20, final velocity is 0. Okay, so right, this is the final velocity, that is 0. So this value is totally 0 minus, that is half, and is m, that is 3, and u square, and u, that is 20 to 20. So this one 10. So this value will be 200 into 3, that is minus 600 joule. So you see, this is the amount of work done. here for finding work done you don't use this formula because their force value is not given, and this work done is negative. What is the meaning of it? Work done positive, that means you are supplying some energy to the system. Work done negative, that means energy taken from the system. When you are supplying energy, you are doing some work, that the velocity increases, so kinetic energy increases. And here you see taken the energy by the system, that is velocity decreases. That's why here negative sign. Okay, now second problem, right? Okay, right, same, a body of mass, suppose here mass given m equal to 2 kg, acted by some force, right, acted by some force which is related to displacement which is related to displacement, right, s equal to 3t square minus 3t plus 5. Displacement given meter, 3t square minus 3t plus 5. You have to find out work done. Find work done at time t equal to 0 second to t equal to, suppose you have to find 2 second. Okay, find it. So same thing here, you see you have to find out work done, but force is not given. You see, force is not given, mass given, and the force which is related to the displacement, and this displacement value is given. So what is the process? That is, you have to use work energy theorem. So use it. So according to work energy theorem, W, that is equal to half mv square minus of half mu square. So at first you have to find out the value of v and u, then you will solve this value. So a is given, so find it. S, that is 3t square minus 3t plus 5. So d dt of s, then you will find the value of v, that is d dt of 3t square minus 3t plus 5. So this one is ds by dt. You see, d dt of 3t square, that is 3 and 2 outside, that is 1. d dt of 3t, that is 3 outside, d dt of t 1, and d dt of 5, that is constant differentiation 0. So this velocity value given 6t minus of 3. Now see, when time t equal to 0, right, at t equal to 0, velocity will be generally initial velocity. So this one will be u. When time t equal to 0, this one will be u. So when here this value is 0, you see t 0, so 0 minus of 3, that is minus 3 meter per second. And at time t equal to this one 2 second, this velocity will be final velocity, and this one will be, you see, 6 into 2 minus of 3, that is 12 minus 3, that is 9 meter per second. Okay, so this is the initial velocity, that is minus 3, and this is the final velocity, and we find this value with the help of this displacement given. So when you know initial velocity and final velocity, you know the value of mass, you can easily use this formula, then you will find out the value of work done. So write W equal to half m, that is given 2, final velocity, that is 9. So this one is 9 into 9, that is 81, minus half into 2, and there is u square. You see u, this one minus 3 the square. So this one will be 81, this one will be minus 3 the square, that is 9. So this value will be 72. So the amount of work done is 72 joule. Okay, now you see here this amount of work done, here this work done is positive. This work done is positive, that means you are supplying some energy to the system. That's the energy velocity increases. Velocity, change in velocity increases. Okay, so this types of problem is important, student. Okay, Let's take another example. Write it. See problem 3. In problem 3, a body of mass m, mass is not given, mass m, acted by some force which is related to its time as t equal to, equation given, t equal to root x plus of 3. You have to find out work done at time t1 equal to 0 second to t2 equal to 6 second. Same thing here you have to find out work done but force not given. So method is same. You have to use work energy theorem, that is work equal to half mv square minus of half mu square. So at first you have to find out v and u with the help of this equation. So you modify this equation, root x, that is equal to t minus of 3. So x will be t minus of 3 the whole square, that is x will be t square minus, this one is 6t plus 3 square, that is 9. Now differentiate it, that is d dt of x is equal to d dt of t square minus d dt of 6t plus d dt of 9. So this one will be dx by dt, that is velocity. This one will be t square, so 2t minus d dt of 6t, 6 outside, d dt of t1 and d dt of 9, constant differentiation 0. Now at time t1 equal to 0 second, when 0 second, velocity will be initial. You write initial velocity u. So t0, that is 2 into 0, 0 minus 6. So initial velocity minus 6 meter per second. Now when time t2 equal to 6 second, you write when t2 is equal to 6 second, here you see the final velocity v equal to 2 into 6, that is 12. 12 minus 6, that is also answer is 6 meter per second. So you use this formula, then you will find out work done. So W equal to half m is not given, okay, write it m, v square, that means 6 square minus of half m u square, that means u hoche minus 6, that means minus 6 square. So you see this answer will be 36 by 2 m, and this one also 36 by 2 m. So here amount of work done, that is 0. Why amount of work done 0? Because you see here velocity, initial velocity minus 6 and final velocity is 6. The magnitude value of velocity is same, velocity constant. When velocity constant, the change in kinetic energy will be 0. When change in kinetic energy 0, that is equal to the work done by the all forces. So here that's why the work done answer is W equal to 0. Okay. Now problem 4 and problem 5. For problem 4, at first you have to know one theory, that is the relation between kinetic energy and linear momentum. Okay. So what is the relation? All of you know the expression of kinetic energy and the expression of linear momentum. Expression of kinetic energy, k equal to half mv square. Now an expression of linear momentum, p equal to mv. Now if I write k equal to half m square v square, so this one will be divided by m, 1 m cancel out, that is half mv square. Now k equal to 1 by 2m, m square v square, mv, that is p, so this only m square v square, that means p square. So this is the relation, v square equal to 2mk, or you can write p equal to root under 2mk. This relation is also important relation, students. This one gives the relation between kinetic energy and linear momentum. Okay, you write, at first you write the basic thing, that is a body of mass m moving with velocity v, then its linear momentum p, that is mv, and kinetic energy k, that is equal to mv square. Then you solve this one. Now with the help of this equation and this equation, you can solve these types of problems, students. I will solve this one and this one will be your homework. Okay, so solve it. Problem 4. You see, in problem 4, which value is given? If the linear momentum of the body increases by 20%. So increase in linear momentum, right? Increase in linear momentum. linear momentum. How much? That is 20% of initial. Suppose initial momentum pi. So increase in linear momentum, this value is given 20%. So that is 20 divided by 100 into pi. So this one will be 5 pi by 5. Okay. Now suppose initial kinetic energy Ki. Formula is P square by 2m. Now when kinetic energy initial, this one also will be initial. Now what will be the final linear momentum? Final linear momentum, right? Final linear momentum, that is PF. Initial linear momentum plus increase in linear momentum. Increase in linear momentum, that is Pi by 5. So Pi by 5. So Pi plus Pi by 5, that is 6 Pi by 5. Now find final kinetic energy. Final kinetic energy. So the formula will be Kf equal to Pf square divided by 2m, that is Pf square divided by 2m. And you know the value of Pf, that is 6 Pi by 5. So 6 Pi by 5 whole square into 1 by 2m. So this answer will be 36 by 25 Pi square by 2m. Okay. For these types of problem, at first you find 4 values. Which one? Initial kinetic energy, final kinetic energy, initial linear momentum, final linear momentum. Okay. You see. Initial kinetic energy, this is the final kinetic energy. Initial linear momentum Pi, increase in linear momentum 20% of Pi, so Pi by 5. So final linear momentum, that is initial plus amount of increase in linear momentum, that is 6 Pi by 5. Now here you have to find out, you see, what will be the percentage increase in kinetic energy. So what is the formula for percentage increase? In upper side there is increase in kinetic energy, and in lower side how much kinetic energy is present into 100%. Okay, so write percentage increase in kinetic energy formula, that is Kf minus Ki, that is the change in kinetic energy, divided by initial kinetic energy into 100%. This is the formula. Now you just use Kf 36 by 25 Pi square by 2m. 36 by 25 Pi square by 2m minus of initial, that is Pi square by 2m, Pi square by 2m, divided by Ki, that is initial, that is Pi square by 2m into 100%. Now solve this one. Okay, so you see in upper side this one will be common, that is Pi square by 2m. So this one is 36 by 25 and there is minus 1 divided by Pi square by 2m. This value is cancel out. 36 by 25 minus 1, this is 25. 36 minus 25, that is 100%. In percentage here you have to use 100%. So this one is 11 by 25 into 100%. So this one is 4 into 11, that is 44%. This is the answer. So what will be the percentage increase in the kinetic energy? That is 44%. Okay. Now problem 5 is your homework. You solve it and send the answer. Tell me the answer in the comment section. Same method. If the kinetic energy of the body is increased by 300%, by what percentage will be the linear momentum of the body increase? Just reverse. Here linear momentum increase given, and you have to find out the increase in percentage kinetic energy, and here kinetic energy percentage given, you have to find out the linear momentum percentage. Method same. At first here you find initial kinetic energy, final kinetic energy, initial momentum, linear momentum. Then you use the formula. Which formula? Here you have to use the percentage increase in linear momentum. So formula will be final linear momentum minus initial linear momentum divided by initial linear momentum into 100%. At first you find Pi, Pf, Ki, Kf. Then use this formula and solve it. Okay. So this is all about our second lecture for work energy power. In next lecture we will discuss I think conservation forces and non-conservation forces. Then we will discuss the potential energy of a string and the expression of potential energy and etc. So today I am ending here.